Hey everybody, happy COVID. I hope you're all doing okay. Let's start looking at examples of smooth manifolds. And where better to start than the original smooth manifold, Rn. And we're talking about Rn with the usual topology. Just plain old vanilla Rn. Well, to be a smooth manifold, first off you need to be a topological manifold. And then you need a smooth structure. So let's look at and remind ourselves what you need to be those things. So there's four things we're going to need to show. First, the three for a topological manifold, right? To be a topological manifold, you need to be Hausdorff, second countable, and locally Euclidean. And to be a smooth manifold, you need a smooth structure. Can we give a smooth structure to our topological manifold? If so, we upgrade it to a smooth manifold. If you take any two arbitrary points in Rn, and let D, this guy right here, be the distance between x and y as usual, right? Just the Euclidean distance. Consider these down here open sets containing x and y, which look like this. Okay, so this first open set I've called U sub x is going to be the open ball, that's what this notation means, centered at x with a radius of the distance between x and y divided by 3. I'm constructing some open sets here. And y is going to be the same. We have an open ball centered at y with a radius that's 1/3 the distance between the 2 points. Now notice that the intersection between these two open sets is empty. I've constructed them to be like that, right? The radius is 1/3 of this distance between the 2 points, which I have written here. That's the distance between the two of them. And since I didn't assume anything special at any point, you can do this for any two x and y in Rn. For all points in Rn, there contains an open set for those 2 points, so 2 open sets, one for each point, such that the intersection is empty. And that's what it means to be Hausdorff. All points are distinguishable, is how you might say that heuristically. Heuristically? I think that's the right word. So next, let's look at second countability. So consider this basis for the topology of Rn, where it says take all the open balls centered at Q of radius r, and what is Q? Q are tuples, n tuples, right? All points in Rn are going to have n components, and each of the elements in that tuple are rational numbers, and each of the radii are rational numbers. So this is the basis of rational radius open balls at points with rational coordinates, and this is a countable basis for Rn. So a countable basis exists because we found one. Therefore, Rn is second countable. Alright, now let's show that it's locally Euclidean. So consider the single chart where the open set is Rn and the map is the identity map. Since Rn is an open set in Rn, and also Rn covers Rn, right? This open set covers the entire space. So this single open set is an open cover for Rn. Now, the identity map is continuous. You can take that as a math fact. I'm not going to prove it here. Hopefully it's fairly intuitive. So this single chart is an atlas for Rn, right? Rn is locally Euclidean. Well, technically we haven't showed that it's an atlas. We've just showed that there is a homeomorphism, the identity map, that takes this open set from our manifold, which is Rn, to Rn. The logic here is almost circular, but hopefully this all makes sense. I misspoke. The atlas comes in a second when we talk about compatibility of all of the charts, of all one of the charts. So now we're going to show that Rn is actually smooth. Because in fact the identity map, taking a point and give back that point, is a smooth function from Rn to Rn. And it is vacuously compatible with all the other charts on Rn because it's the only chart on Rn. So Rn comma identity is a smooth function on Rn. And just a note here, the inverse of the identity map is again the identity map. So it's bijective and bicontinuous. This single chart is a smooth structure on Rn. Since Rn satisfies the above four conditions, the 3 to make it a topological manifold, and this fourth one to upgrade it to a smooth manifold, then we see that it is indeed a smooth manifold. Thank you very much for watching, and in the next video we're going to go through an example of a smooth manifold that isn't quite so obvious, and I think that'll really bring a lot of the things that we've talked about in the earlier videos together. So stay tuned for that one.